All right, today we're going to focus on synthetic applications of substitution and elimination reactions. We've been talking a lot about these reactions in class, and I gave you problems to do for Monday where you're going to have to apply some of the things we've talked about and some things that we haven't yet talked about. So I wanted to give you a little preview of that so that you'll be a little more comfortable on the problem set and you'll be ready to focus on the key chapters in the book and then talk about what we're really interested in on Monday. All right, so the key sections for the problems you're going to do for Monday are the following. All right, so they're in a couple of different chapters. All right, so first is 13.9, and that's going to be reactions of alcohols. And that's going to get at some of the stuff we talked about today where we're thinking about making alcohols into good leaving groups so that we can then do a substitution reaction. And we'll do some examples of that in just a minute. Section 14.8, which is preparation of epoxides. And we talked a little bit about this in class today when we were looking at the van der Waal paper where they made an epoxide by an intramolecular SN2 reaction. Right, and there's some more discussion of that in the book. And then 14.10, which is ring opening reactions of epoxides. And we've talked some about reactions of epoxides in Chem 222, but we're going to go into more depth this semester. So it's probably not a bad idea to review your notes from epoxides from last semester and also note that on the daily problems we have some reactions of epoxides, and one of the reactions we're going to talk about from the van der Waal paper in class on Monday also is a reaction of an epoxide. So make sure that you take a look at those sections so you're ready for those discussions and those problems. So what I want to do also is remind you of something that we talked about last semester but will be especially helpful on this problem set. So you also want to review reactions of nitriles. And again, remember, nitriles are C triple bond N, so we also call these things cyanides, but reactions of nitriles are section 21.13. Those will be important for the work that you're doing for Monday. All right, so I just want to give you a couple of examples just to see some of these reactions and hopefully give you a little more comfort when you're doing the daily problems. So, for example, here's the sort of problem that we're interested in looking at. It combines a lot of the stereochemistry we've been talking about with some of these reagents that you're going to find in these chapters. All right, so one really interesting problem is something like this, where we want to take this enantiomer of this compound and turn it into two different products. All right, so the question is, how can we take this and convert it into this trans compound? How can we convert it into this cis compound? Right? What reactions would we use to do these two different transformations? Right? Which I think is a really important thing for us to know. And when we think about retrosynthetically, we're going to want to put the cyanide in as sodium cyanide. That's going to be an SN2 reaction. So the question is, what do we react it with so we can get the stereochemical outcome we want? We also notice that we have an OH. OH is not a good leaving group, so we're going to need to modify that OH so we can turn it into a good leaving group. Right? So one of the strategies that you're working with in lab is turning it into a tosylate. Right? So we can fill in this top arrow if we think about one, reacting this with tosyl chloride and pyridine, and then two, reacting it with sodium cyanide and let's say DMF. All right? The key point here when we do this set of reactions is that we're going to end up, after the tosyl chloride reaction, making that molecule. Right? And when you do the reaction with tosyl chloride, you don't impact the stereochemistry of the carbon-oxygen bond. All right, and that's a really important question that I'd like you to consider. Why, when you do this reaction with tosyl chloride and pyridine, does nothing happen to that? All right, make sure you can answer that question. And then when we do the second step, when we add sodium cyanide in DMF, here's our SN2 reaction, which goes by inversion and gives us the product we want. All right. On the bottom, we have a situation we talked a little bit about in class where we want to get a retention reaction. All right, and we talked about in class how to do this. We're going to have to do two different SN2 reactions, right? So that we can do an inversion followed by another inversion, right? And so the way to do this reaction, or this series of reactions, is to first react with PBr3 or SOCl2. All right, I'll let you look in the book to look at the mechanisms for these reactions. All right, they're both SN2 reactions. They're a little bit complicated, but something that you can easily understand. Right, make sure that you take a look at those reactions, and then it'll be sodium cyanide. Right, and so when we think about what's happening here in the first reaction, if we use PBr3, we will end up making the bromide with inversion. So that's the result of the first SN2 reaction, where we get the corresponding bromide with inversion. Then we do the sodium cyanide reaction with DMF. And again, we get our second SN2 reaction with inversion. So this is a really important strategy for us to be able to control the stereochemical outcome, knowing that if we use the tosylate, we can keep the stereochemistry the same at the carbon-oxygen bond. If we use PBr3 or SOCl2, we'll get inversion to give us a leaving group. Right? So a very useful strategy. The final thing I want to do is talk about reactions of epoxides as just a preview for what you're going to work on the daily problems for Monday. So let's look at something a little bit simpler than what you have in the daily problems, but I think will illustrate the key points. Right? If we're thinking about this epoxide, and let's think about if we're going to do a reaction with sodium methoxide, and let's say it's in DMF. Right? We've talked about how reactions of epoxides are SN2 reactions, and this is a great example where we have a strong nucleophile / base. So this is going to be an SN2 reaction. When we think about which bond we're going to, or which carbon we're going to attack in the epoxide, we know that SN2 reactions are dependent on sterics, and so we're going to attack the least hindered carbon. So we'll attack with methoxide at this carbon. So we'll attack the least hindered, and we'll react with inversion at that carbon, and we'll open up the epoxide. And I know this isn't a stereocenter, but if it were, we would make sure that we had the OCH3 coming in from the back, and then we can add an acid quench to give us our product. All right, so SN2 reaction. The other way that epoxides can react is that they can react with acid. Right? So another way to get these things to react is to have sulfuric acid and methanol. Right? And when we do these reactions, they react quite differently, and it's important to recognize the difference. Right? When we have acid and an epoxide, like we do in all of our acid reactions, we're going to protonate the epoxide. Now, this epoxide is in equilibrium, and we can open it up so that we can relieve the ring strain and form a reasonably stable carbocation. So Again, this bond is still coming out. We can form that carbocation. And interestingly, there's a partial bond here. And I'm hoping that this looks something like an intermediate that we've seen in alkene reactions. All right, so I want you to relate this to an alkene reaction that we studied last semester. Right now, methanol can attack this carbocation. And it will attack from the side opposite of the carbon-oxygen bond here because that's blocking the front face. So the methanol will attack from behind. And then we can just do a proton transfer. And we can end up with our product. Right? And in this reaction, it's very interesting because we have SN1 regiochemistry, meaning we're attacking the more hindered carbon because we go through a carbocation intermediate, but we have SN2 stereochemistry, meaning that where we attack, we get inversion because the oxygen is blocking the top face where the epoxide was. Right? So definitely think about these conditions, these two different outcomes, and you'll see this on the daily problems for Monday, and we can talk about it more in class.